standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Allumage décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
An international collaboration between NASA, ESA, CSA, and other scientists from 14 countries. A project that was prepared for almost 20 years. Mirrors 6.25 times the size of Hubble's, and a window seeing back into the cosmos. The James Webb Space Telescope, also known as Webb or JWST, was launched December 25, 2021 in French Guiana on an Ariane 5 rocket. With over 100 successful missions, it is one of the world's most reliable heavy-lift vehicles capable of delivering the $10 billion infrared time machine to its destination, the second Sun-Earth LaGrange point, or L2, where Webb can be shaded away from the heat of the Sun, the Earth, and the Moon, while remaining in the same general location relative to Earth, assisting communication. JWST is actually too large to fit inside any rocket fairing, so it needs to be folded within the Ariane 5, kind of like origami. Hence, a complex deployment sequence must be done before it begins its observations. Ariane 5 provides thrust for roughly 26 minutes after liftoff. After upper stage engine cutoff, Webb is released from the Ariane 5 and is flying on its own. About 33 minutes after liftoff, the solar panel is deployed, and the telescope will go off from battery power and start generating its own. About 1 day after launch, the antenna will rotate so that it is pointed towards Earth. This is the automatic deployment that will allow commands for all other deployments moving on. About 3 days after launch, the sunshield pallets, which supports the 5 sunshield membranes, folds down and activate heaters to heat core components for deployment. This marks the start of sunshield deployment and all major deployments. About 4 days after launch, the entire core of the telescope extends 1.22 meters. This movement provides separation between the spacecraft and the telescope to allow better thermal isolation and room for the sunshield membranes to unfold. About 5 days after launch, the aft momentum flap deploys. It is used to help offset some of the solar radiation pressure that affects the spacecraft due to the large sunshield. This helps to minimize fuel usage during the mission. Then, the protective membrane of the sunshield gets rolled up. About 6 days after launch, the sunshield extends fully with a motor-driven movement. About 7 days after launch, the 5 layers of the sunshield tensions and fully deploys. About 10 days after launch, the secondary mirror structure is moved into its operational position. About 11 days after launch, ADER is released from its launch locks and deploys the cooler for instruments on board. About 12 days after launch, the folded wings of the primary mirror, each holding 3 of the 18 mirror segments, unfolds and latches into place. After tuning individual mirror segments, the telescope will make its own mid-course thrust correction to the second Sun-Earth LaGrange point. When these major steps are successfully done, the James Webb Space Telescope will be fully deployed and ready for its journey. JWST itself is a technical marvel. the 6.5 meter mirror, made of 18 hexagonal-shaped mirrors 1.32 meters in diameter, is the biggest ever sent to space. In fact, it is so large that it has to be folded up to fit in the Ariane 5. But the primary mirror is not the only mirror. JWST runs a 3-mirror system, with the primary mirror reflecting light onto the 0.74 meter secondary mirror by utilizing its actuators on each of the 18 segments, which then focuses the light onto the tertiary mirror. This is known as the aft optics subsystem, which is at the back of the primary mirror. The tertiary mirror then sends light to the instrument through fine steering mirrors. But why gold, you might ask? Actually, the mirrors of JWST are primarily made of beryllium, only coated with a microscopic layer of gold that is only 700 atoms thick, which is 1,000 times thinner than a human hair. While beryllium provides light weight, gold is ideal for reflecting infrared light, close to 99% to be exact. Webb's kite-shaped sunshield is approximately the size of a tennis court. In this 5-layer sunshield, the outmost layer is 0.05 millimeters thick, with the other 4 layers being 0.025 millimeters thick. The purpose of the sunshield is to block heat radiated from the sun, the earth, and the moon to ensure that the infrared-sensitive instruments operate in very cold temperatures so that the heat does not interfere with them. It works not only through reflecting the heat directly away, but also between layers, each layer being an insulation and reflecting heat in between, then outwards from the spacecraft. Through this structure, the spacecraft can have its hot side at about 120 degrees Celsius, while the cold side negative 235 degrees Celsius. There are 4 primary instruments on Webb, with the near-infrared being NIRCam, NIRSPEC, and FGS and NIRIS, and the mid-infrared being MIRI. This provides 3 primary modes in which Webb can operate in: imaging, spectroscopy, and coronagraphs. NIRCam, or near-infrared camera, is Webb's primary imager and provides high-resolution imaging and spectroscopy. It is also equipped with coronagraphs, which allows the observation of dim objects around a bright object by blocking the light source, like how we can see the corona of the sun during solar eclipses. NIRSPEC, or near-infrared spectrograph, is designed to observe the spectrographs of 100 objects simultaneously. If the entire image is captured, however, the amount of data will be so immense that Webb will not be able to process. This is why scientists created the microshutter array, a shutter system with individual cells each as wide as a human hair. They have lids that open or close with magnets and can be individually controlled to block a portion of the sky and only observe the useful parts. The near-infrared slitless spectrograph and fine guidance sensor has imaging and spectroscopic abilities. NIRIS is able to capture images of bright objects at a resolution greater than the others, while in the same housing is FGS, a camera system to make sure Webb is stable and pointing in exactly the right direction throughout the observation by identifying guide stars and locking onto them. The mid-infrared instrument, or MIRI, is what scientists rely on to study redshift, newly forming stars, faintly visible comets, and the Kuiper belt. This is because it operates in the mid-infrared spectra and can capture images with both the camera and the spectroscope. This allows the mapping of spectra across a field of view. Because MIRI sees farther into the infrared spectra than the other instruments, it has to be kept even colder than its counterparts. To do this, scientists created the cryocooler, a giant helium refrigerator that keeps MIRI chilling at -266 degrees Celsius. The James Webb Space Telescope provides us with numerous ways to observe the universe. Studying infrared essentially allows us to see further back in time due to redshift. Moreover, light of longer wavelength also tends to penetrate dust more easily. With the sensitivity and resolution of Hubble and the view of Spitzer, we can observe the earliest universe, almost 13.5 billion years ago, to where it all began, the reionization epoch, the first galaxies, their evolution, and the formation of stars and planetary systems. By studying the emission and absorption spectra of galaxies and objects through spectrographs, we can reveal which molecules and elements it contains, because different elements emit or absorb different frequencies of light. With the capability of observing 100 objects at once, we can measure physical and chemical properties of planetary systems and investigate possibilities for life. There are still numerous unexpected possibilities for us to explore with the James Webb Space Telescope. With its capability of identifying the heat signature of a bumblebee at the distance of the moon, more questions and discoveries are sure to come.